The next speaker is Crystal Guido. She is the fruit crop entomologist and extension specialist at UW-Madison, and she's going to talk about pest management on apple.
Good morning, everybody. So it's going to be a little tricky because I got to look at my slides back, so we'll try to make it work. So I was asked, I kind of asked the Apple board what they wanted me to talk about because I wasn't sure what you guys were interested in. I had a couple requests and I focused on apple maggot. So I'm going to tell you about the basic biology of apple maggot and then about a study from 2012 that can be applicable to you. And then I'll talk to you about brown marmoset sting bug after that. So, okay. So apple maggot, I hope you guys all know what they look like. They're in the family Tephrididae, so they would be our fruit flies, right? A lot of people call fruit flies those Drosophila, those are vinegar flies, and apple maggot is part of the real fruit flies. So they're flies. On the left-hand side, you have the female, and some of the characteristic, it has 4 white bands, and the male is shorter with a more rounded abdomen and only 3 bands on the abdomen. I'm not going over everything because I'm assuming you guys know a lot about it. But they are a pest that you'll see in the end of June, early July. And they will emerge from the soil. And it's at about 900 growing degree days with a base 50. But there's 2 different models that you can use. And the problem with apple maggot is that they are very much linked to temperature and humidity. So the models are not as clear-cut as you would for, like, say, codling moth. So they're a little bit different, and they don't work as well compared to those kind of moths. Peak emergence is between 1,400 and 1,700 growing degree day. You actually only have 1 generation. Once they start, it's continuous emergence throughout the summer, and it's very much linked to temperature and humidity and soil moisture. And what's very interesting with apple maggot is that during the pre-oviposition period, so before they start laying eggs, when they first come out of the soil, the adults are only interested in feeding on pollen, honeydew, bird feces. They're looking for protein to develop their ovaries to be able to mate and lay eggs. So that period is very critical, and we'll talk about that for monitoring and management. And then 8 to 10 days later, the females are then ready, they mate, and they're ready to lay their eggs. So that's the oviposition period, and that has implications too. So if you look at the oviposition scars, they're very, very small. They're hard to see. The female will just puncture the skin, lay its eggs underneath the skin of the fruit. They lay 1 egg at a time, and they can start laying eggs again after that pre-oviposition period, so 8 to 10 days after emergence. They can lay up to 300 or 500 eggs per female. And if you look at this slide has a lot of oviposition scars. And so if you look here, you have this sunken area, but it's kind of hard to tell, especially when you have those lenticels, to see where the oviposition scar is, where the egg was laid. And so if you look up closely, this is actually where the oviposition scar is. So what happens is as the female lays its eggs underneath the skin of the fruit, the flesh of the fruit near that, where the larva will start feeding, doesn't develop with the rest of the fruit. So you have that scarring that will occur. And so if you if you do a lateral cut of the fruit, this is what you'll see. You have those very faint brown trails in there. The larvae are very small and tiny. They're hard to find. That's why they are called the railroad worm in part of it, because of those trails that they make. But then as the larva continues feeding on the fruit, that's when you definitely can see the damage. It's much easier to see as the larva gets bigger and gets substantially rotted. And what happens is that the fruit will then drop to the ground, which is perfect because the larvae tend to go out of the fruit and go pupate under the leaf litter. So it's perfect for them. And they'll pupate in the top 2 to 3 inches of the soil. So when it comes to monitoring the flies, you want to be doing, so you can do visual inspection. Those flies are pretty conspicuous, and I didn't put up the slide where you have the wing patterns, but it's kind of that W or kind of F pattern that you can see on the wings, the black pattern. And so you can look for the flies, but then you can hang traps, right? So towards the last week of June, you have 2 types of traps that you can hang. So if we go back to the biology, that oviposition period, it's very important to think about that. If you do those yellow sticky cards, and I'll show you pictures of that after, and you can bait them with a feeding attractant. It's an ammonium lure. The yellow sticky card, the idea is that for insects, they look the same than foliage. They have the same color that the insects see foliage. So they will attract those pre-oviposition females. And the feeding attractant lure attracts them when you're looking for that food, that protein, to develop their ovaries before they're mating. Then after that, when we're done with that pre-oviposition period, what you're looking for is a place to oviposit, to lay their eggs in. So then you're looking for the fruit. And that's when we start using those red spheres. Some can be baited, some are used also unbaited. And then at that point, we're looking at different attractants. Here it will be a ripe fruit lures that target those females that are mated and are looking for an oviposition site. So these are the yellow sticky cards. Obviously, they attract a lot of insects. So you have to be very careful on how you identify your insect. And that's the key to any kind of integrated pest management, is obviously knowing what insects you're looking at. And then these are the red baited sticky sphere. Here, this one is not baited. But the idea is that you have this tanglefoot, this sticky material. And if you can have the lure that you can see up here, but even without the lure, they still work because the females are looking for those fruit, and then the killing agent is that sticky material, right? So they get stuck on there, and that's how they die. So of course, as you can see on the right-hand side, you're going to have a lot of insects that are glued there, and it's kind of messy business to deal with those spheres. So there's different options you can do. Trap out has been one that's been suggested for apple maggot. So it's best when you have low densities of flies. And you can use those sticky spheres with the lure, about 1 trap per 100 apples. So that gets very extensive kind of trapping that you need to do. But perimeter trap out seems to work, right? There's been studies that have shown that that's working if you do it in the perimeter, as a lot of them are coming from outside your orchard. And then you want to have interior traps that will check that your perimeter traps are actually working and preventing your flies from establishing in your orchard. But it's, as I mentioned, labor intensive when you're talking about 1 trap per 100 apples. And you need to clean the traps at least bi-weekly. So that's very labor intensive. So the study I wanted to talk to you about comes from 2012, but I haven't talked to you about it, so I think it's a very interesting study. And what the title of that study is Integration of Insecticidal Phagostimulatory, so that means it stimulates feeding, and visual elements of an attract and kill system for apple maggot fly. So it stems from, and you have the information down there if you want to find that paper, but it stems from the idea of the red spheres, right? So that's from the people the same lab than the people that started this whole Propokis, the person that was starting that for apple maggot. And so the idea is that these spheres are time-consuming, everything I just mentioned in the previous slide. And so there had been development from that same lab in West Virginia where they looked at, so this is a black and white picture from that paper, but this is a red sphere too. And on top here, you have a cylinder, and that cylinder, what they did is, so that's not this paper, right? I'm just giving you the background here. They put in that cylinder some sucrose. So they would attract the flies when they come, not attract, the flies will come to the red sphere and get stimulated, that phagostimulatory, they would get stimulated to feed. And you can put then an insecticide on the red sphere and kill them. That will be your trap out. As they come in, you kill them. And so you don't have any more a sticky material there. You're just killing them as they touch the sphere. So that was, step 1 was the red sphere. Step 2 was that sphere with that sucrose solution on top. But there's a limitation with that. And one of the big limitations to that is that the cylinder on top is sugar. The insecticide is on the sphere. And what they found is a lot of flies would go onto the sugar part of the trap and not actually go to the sphere. So they went the next step further, and that's what this study is about. So they compared this red sphere topped with the cylindrical cap, and then this one, so it's hard to tell, but there's a cap here that's embedded onto the sphere, right? So it was part of it is visual cues, looking if the red sphere is best for attracting the flies, and it actually wasn't a problem with the cylinder, but they wanted to do that, and what they did is, in this case, they did two things to improve from the previous design. The sugar is included in that top cap. Can you see this part here? Here, this half, well, not half, but moon-shaped thing. This has the sugar, and the concentration, they do 20% wax, 80% sucrose, and then they added Entrust, so that would be organically approved and works really well, and they put all that on there, right? So we have both the sucrose and the toxicant that's on the sphere. And so the idea with this is that the sugar is on there, but it has to be released, right? And because of the Midwest, Northeast, there's a lot of rain. So the rain is the one that's going to release the sugar onto the sphere and get the flies to be stimulated to feed on those spheres that have then the toxicant, your insecticide. Make sense? So they did some lab assays and then field trials. So I'm going to start with the lab assays. And so here, they looked at it from the standpoint of the sphere with the cylinder, and they did different concentration of that spinosad, so Entrust. And so on the y-axis, you have the percent mortality of the flies, and on the x-axis, it's the amount of rainfall to see how much they can take of rain before it's just not working anymore, and how is the efficacy acting with the rainfall, which is very important for us in areas where we have a lot of rain. So what they found here is that there was a significant effect on the concentration of the insecticide. So you have here, the control is the line that would be at the very bottom, and everything up is the step up in concentration. So they did it in a power of 10. And so obviously, here what you can see on the data is that the higher concentration got the highest percent mortality, and it decreases significantly with the decrease, mortality decreases with the decrease in concentration. And it drops down from rainfall events, right? So they simulated that in a cage study. So we have an effect of the concentration and also on the amount of rainfall. So the percent here, the maximum is 1%, and we're at above 85% mortality throughout all the different rainfall events that they simulated here. Here, we're looking at this other type of sphere, right? The one that they're really addressing here, it's to see if that's working. Oh, I forgot to mention, how do I go back? Oh, yeah. I forgot to mention on the rainfall here, they went up to 25 centimeters of rainfall. And that's obviously a lot of rainfall, so that was over several days that they did that. It was a maximum of 2.5 centimeter per 24 hours that they were applying. So you can see 25 centimeters, they stopped there because that's the average rainfall they get in West Virginia. Here, it's the same thing, it's a percent mortality. The concentrations are a little different. The top one is the 1%, so it's the same, the maximum than they had in the previous study. And then they did 50%, and then 10th, and then 100th, and the control. And on the rainfall, they went further. They went all the way to 45 centimeters of rainfall. So your 25 would be somewhere around here to compare with the previous one. And what they found here is that at the 1% concentration, they held to 100% mortality with this design, all the way to 30 centimeters of rainfall. So it holds really well, okay? And then when they did the 0.5%, they still had, it's not significant from the 1%. So with half of the concentration of what they had in the previous test, they still get about 100% mortality. So very, very promising. For the lower concentration, if you look at them, after the 7.5 centimeters, and they don't talk so much, I don't think it's significant of why it drops like that, but then you can see that it increases even with the 10th percent, we're almost at over 90% mortality. So this system is working really well. So this was, again, done in the lab, and so what they did is they went into the field. So they did field assessments. The plots were 2 hectares, and they had 4 different farms. And they did a perimeter deployment, 8 meters apart for 28 traps total per hectare. Okay, so perimeter trapping. And in the middle of that, they put the unbaited regular stichosphere just to have a way of checking what the population, just as I mentioned before for trap out, you would put those spheres in the interior to see that your perimeter trapping is actually working. So what they found here, there's the different sampling dates on the left-hand side here, and here are the 4 different farms. What I surrounded in red are the treatments where they put those spheres. So again, it's the sphere, the better sphere that they're testing, right? I shouldn't say better. The one they were hoping would be better, but seems to be so far. And they, so that little cap, not the cylinder. And they put those traps, and then in the other plot, in the same, at the same orchard, they did insecticide spray. So they compared the 2. And what they found is, what they're looking at here is the mean number of apple maggot that are caught on those interior traps that are not treated, that are just red sticky sphere to just check the population levels. And at none of the times did they, so they reached the 2 flies per sphere is the threshold for spraying there. And they went to that, but they never sprayed. The growers never sprayed in the treatment where they had the spheres. They let it go. And they reached the same number of time above that threshold with an insecticidal spray on the entire plot than they did with that perimeter treatment on the outside with no insecticidal spray. And overall, what they found is that there was no significant difference. It was never at any of the farms that they did that, they had a significant difference between the insecticidal spray and the, and right now, unfortunately, I can't remember what the insecticide they used, but what they had was the spheres. So no insecticide at all, and exactly the same amount of control that they were getting at those 4 farms. Then they looked, obviously they collected some fruit to look at damage and infested fruit. And they collected 10 fruit per tree from 40 different trees in each plot. And they just looked at the percent injury. And here, same thing, for the 4 different farms, no significant difference between the sphere as a treatment versus the conventional insecticide plot. In all cases, they never reached more than 1.25% injury, okay? So, overall, what they found here, and this is the conclusion for this study, that contoured cap, this provides longer longevity, as I showed you in those lab assays. And it's, even with half of the material, it's still as efficient as what you would get with the full amount of material with that cylinder that they were comparing it to. The rate of mortality for those lower concentrations increased with the amount of rainfall. For the higher concentration, it was at 100%, so it can't go any further. But for the lower concentration, it increases with rainfall. And with the cylinder, it was actually decreasing, if you recall the graph, with the amount of rainfall. So there's a wire guard, I didn't talk about that, but how they put that sucrose and wax, they compress it. It's a kind of an interesting process. They put a food dye in there, and then they put a guard, a wire guard that's embedded on the exterior of the surface, and that protects the sphere, the sugar, from invertebrates that could be, or vertebrates, I mean, that could be going there and feeding on that, because they've had issue with that, so they took care of that at the same time. So I talked to the people last week that have developed this, and I was asking them, so where is this at? This was published in 2012. Where are we at with this technology now? Because it seems pretty promising. It's obviously something that can easily be manufactured if a company picked it up. The spheres are already sold, so why isn't it out and available for growers? And so Tracy Lesky, who's working at West Virginia with the USDA, was telling me that there was problem with the insecticide, with that formulation of interest, and the company wasn't really following through. And I think it's a wettable powder. It doesn't say in the paper exactly what it is. But they weren't really following through, so they thought that was going to fall out. And then the same lab is working with those same spheres for spotted wing Drosophila. And that's a huge market. So she said that the company is, again, really interested in this technology, and that could go further for treatment for apple maggot, or management, I mean, for apple maggot, because of the interest for spotted wing Drosophila. So there's great hope in this technology being available and maybe getting to the commercial use for you guys to purchase and test in your orchards. So I hope that's going to be something in the near future that we'll see available commercially. Okay, so moving on to other methods. You all know about kaolin clay that is available for apple maggot treatment. The idea is you cover your fruit with this diatomaceous earth. It's just natural powder that you find. It's a degradation of shells and stuff, like it's old earth, right, kind of thing. So you cover your fruit. It has its issues because obviously as the fruit grows, then you have to reapply. As it rains, you might have to reapply. But the idea is that it will deter the fly from laying eggs on there. It doesn't kill the fly, it just deters them from laying eggs on there. So it works, it's just time consuming. And then for chemical control, there's action thresholds that are different. If you use the yellow sticky card or the unbaited red sphere, then you would go with about 2 fly per week before you start applying an insecticide. And for the baited red sphere, because they're more sensitive, you can go up to 5 flies per week before you apply an insecticide. And here are just a list of insecticides. I hope you all got your spray book so that you can go back and refer to that for your sprays. But here I gave you some of the efficacy of those different insecticides that you can use, and pre-harvest interval, and kind of the residual activity that you would get with those different compounds. So again, check the label and do all your homework before using any of those insecticides. So I want to move on now, and I don't know how I'm doing on time. Okay, thank you. But I want to talk to you. Last year I gave you a talk about brown marmoset sting bug, so I'm not going to bore you with the same thing that I did last year. But what I want to talk to you about is you guys have funded us in the past to do some insecticide trials that we're doing at Peninsula Research Station, and we were testing some of those soft chemistries up there. And so this year, what we are very interested in asking you guys to fund is looking at brown marmoset sting bug. So just a quick overview of what it is. And I don't know, I brought one that I caught at my house, but I don't have it. So I'll have to see if I can get it. I don't see the person that was supposed to bring it. But the characteristics for that are, here it's a smooth shoulder. Some of the sting bugs have a jetted edges on their shoulders. The main part is the white bands on the antennae, the alternating colors on the outside of the abdomen here between brown and white. Then there are a sting bug besides that. So if you squish them, which I did, they smell. So nothing too surprising here. But the adults would emerge in the spring, in late March through June or so, depending on location. And it will be based, again, on degree day accumulation. And we probably only have one generation in Wisconsin. So this is the map that they put together. And interestingly enough, that's done by Tracy Lesky, the same person that has a lot of work on brown marmoset sting bug. And this is on a website called stopbmsb.org. So you can go there and check it out. And they update the map regularly. So on this map of the US, what you have is in green is where it's been detected. So if you see Wisconsin, we're green. It's been detected in Wisconsin. We know we have populations in Wisconsin. In yellow, it's a nuisance problem only. So they're coming into people's houses, but that's it, which is not a good thing, but it's not going into agricultural crops. In the orange, it's agricultural and nuisance problems. And then in red, it's severe agricultural and nuisance problem. It was first introduced in Pennsylvania. And as you can see, it's spreading. We first detected them in 2010 in Wisconsin. Michigan also detected them in 2010. And you can see this year, they just moved to the orange setting. So they're not a nuisance problem, they're now a nuisance and agricultural problem. So what happens in every state where there's a problem with brown marrow sting bug, you go a couple years with it's detected, it's there, we know. We see them around houses, then the numbers start building up. And then once they pass a certain, we don't have a threshold for that, but a certain number at some point, that's when they start going into agricultural crops. We're 5 years from the first detection. We're getting to that point of the numbers going up. At my house, I caught about 10 on my window in October, and I was talking to different people in the state that look at that, PJ Leash, or insect diagnostician that gets all those phone calls and samples, noticed also an increase in those records. So for Wisconsin, this is what is confirmed now, but these are only confirmed based on people sending us a sample, a picture, nothing that we are actively looking for. Actually, DATCAP has an active monitoring program, and they haven't caught anything yet. But here, what we're interested in doing, so you see very few counties, but it doesn't mean that that's all we have. We just don't have reports from other places. So this year, Krista Hamilton from DATCAP, Peter Wertz from IPM Institute, and I had multiple conversations. And what we think is that we've reached that level, as I mentioned, from Michigan, where the numbers are building up. We're still in urban areas where they're building up. We have a zero report of, although there might be one today, but we'll have to confirm that. So far, we have zero report in any agricultural crop, okay? Now is the time to really start monitoring in those agricultural crops and see what's going on. If there's going to be a year where it could start, it's going to be this coming year. So we all think, IPM Institute, DATCAP, and myself think that we need to work together to really go and check in apple orchards, and if people are interested that are in vegetable crops or field crops, we'll be more than happy to coordinate that too. But what we want to do is really target apple right now and see, are we seeing those BMSB showing up there? Even if it's in very low numbers, so we can really alert you guys and let you know, okay, now it's the time to really pay attention, and they're coming. There's a lot of what a lot of people would think are lookalikes. So if you're not a collaborator, for collaborators, we'll provide all the support you need. But if you're not a collaborator and you don't know, but you want to know, please send us a picture, send us the sample. We'll be more than happy to tell you, because we want to know for your sake, but for everybody's sake. So if you get anything and you're suspecting it could be, don't hesitate to send me an email or any of those people I mentioned, or PJ Leash, the insect diagnostician. We all talk amongst each other. So we'll be able to keep track of that and help you make sure the one in the lower middle here is BMSB, and it's not necessarily easy for an untrained eye or somebody panicking. So we'll be happy to give you some information of what it is. And so PJ Leash, the insect diagnostician, can help you. And Rutgers University has a big program there, so you can report to them if you want to. But report to us, that would be great. Thank you very much, everybody. If you have any questions, thank you.